beginning the lesson of resistance. In this lesson, we're going to understand the equation of resistance in relevance to voltage and current, know an experiment to determine the resistance using a voltmeter and a meter, and state qualitatively the relationship of resistance of metallic wire to its length and cross-sectional area. Let's start. What is resistance? Resistance is nothing but the opposition of current, trying to slow it down. So resistance occurs because the free electrons flowing in the circuit, which are current, collide with the metal ions in the wire. These collisions slow down the electrons and resist their flow. The higher the resistance of a circuit, the lower the current. This means that good conductors have low resistance and good insulators have high resistance. The resistance of a circuit can be increased if you add more resistors or variable resistors to it. Every electrical component has a resistance, even the wires themselves. So, if there is a high resistance, low current will pass through, and if there is low resistance, high current will pass through. Now let's talk about Ohm's law. Ohm's law relates between voltage, current, and resistance, where V is equal to IR. And remember, voltage is measured in volts, current is measured in amperes, and resistance is measured in ohms. It's written as so. So current, potential difference, and resistance all affect one another. Changing any of these will change all of them. Current and resistance are inversely proportional. So if you increase the resistance, current decreases, and vice versa. So if the resistance is doubled, current will be halved. This relationship is known as Ohm's law. Resistors are used in circuits to control either the current in branches of the circuit or the potential difference across certain components. This is due to the consequences of Ohm's law. Because the current in an electrical conductor decreases as the resistance increases, and the potential difference in an electrical conductor increases as the resistance increases. So basically, I will become less if R became more, and V will become more if R became more. Okay. So if I have a 12 ohm resistor with a current of 0.3 ampere, what is the potential difference? I'll use my equation. V equals I times R, 0.3 amperes times 12 ohms to give me 3.6 volt. Be very careful that this is ampere, because sometimes in the question they give you milliampere or microampere. And of course, you know that milli is times 10 to the power negative 3, and micro is times 10 to the power negative 6. Okay. Current voltage graphs. The relationship between current and voltage difference of a component can be shown on a current voltage graph. When the relationship between current and potential difference is linear, we find that the IV graph is a straight line passing through the origin, but here the resistance is of course constant, and these are known as ohmic resistors. When the relationship between current and voltage is nonlinear, that means it's not a straight line, the resistance is not constant, and these are known as non-ohmic resistors. So here the resistance is constant, it's an ohmic resistor, and if the resistance is non-constant, it's a non-ohmic resistor. Here is a current voltage graph of an ohmic resistor, like this one. And here the resistor is fixed, as we said, at a constant temperature. It has wires also at a constant temperature. And you can see that the relationship is linear. If it's a nonlinear IV graph, which is a non-ohmic resistor, as shown in the second picture, This usually happens in filament lamps, diodes, LDRs, and thermistors. So the relationship between current and voltage for a wire or a fixed resistor is linear or directly proportional, meaning that the voltage will increase as current will increase or vice versa. But make sure to know that in that case, the resistance should be constant. This is the graph, the IV graph for a wire of a fixed resistor. As you can see, it's a linear relationship. As for the filament lamp, which is a non-ohmic resistor, the relationship is not a straight line, it's nonlinear. So this means that when voltage and current increase, they don't increase at the same amount. The IV graph for a filament lamp shows as voltage increases, the current increases at a proportionally slower rate, and the resistance increases the flatter the slope, like here, the higher the resistance. So the more flat the slope is, that means that the resistance here was high. Okay? This causes an increase in resistance as it becomes more difficult for electrons to pass through. Since resistance opposes current, this causes it to increase at a slower rate. A diode allows current to flow in one direction only, which is called a forward bias. So in the IV graph, as you can see, it only increased on one side, which means that this is a forward bias. And this increase in voltage and current shows that the resistance here is very, very low. However, in the reverse direction, the diode has a very high resistance and therefore no current flows. This is called a reverse bias. As shown in the IV graph, that the V became 0. As for the wire, as the electrons are passing through, they collide with the metal ions in the wire, and this transfers energy away from the kinetic store of the electrons, making them slow down. That's why we said wires have their own resistance. The energy from the electrons is transferred to the kinetic store of the vibrating metal ions, causing the vibration to increase, causing the temperature to increase, and therefore heat is lost and the current becomes less. If the wire is longer, here we need to talk about the length and the cross-sectional area of the wire. The longer the wire, imagine it as a race. If I asked you to move from point A to point B, or from point A to point C, which one will reach faster? Of course, A to B, because it's shorter. A to C will take a longer time. Think of it the same way. If the wire is longer, each electron will collide with more ions, so there will be more resistance, and therefore less current will flow through. However, when we're talking about cross-sectional area, imagine if you're passing through a small opening here in a wall versus a large opening in a wall. If you are 10 people and if you are 10 people, which one will allow the 10 people to pass through easily? The one on the right. Same thing. If the wire is thicker, there is more space for electrons and more electrons can flow. So the thicker the wire, the less the resistance, the more the current. Finally, the relationship between resistance, length, and cross-sectional area can be represented mathematically as well. Doubling the length will double the resistance and vice versa. Doubling the cross-sectional area will halve the resistance and vice versa. That's all for today. Please let me know if you have any questions and have a wonderful day.